Thank you for viewing my REACH seminar presentation. My name is Tai McClellan Maaz, and I will be covering a few concepts that I explored in my PhD dissertation under the direction of Bill Pan on rotational nitrogen cycling. So hopefully this presentation will eventually lead to some discussions on how we can construct nitrogen balances and assess nitrogen dynamics across the various agroecological classes that we have for REACH. I wanted to start off the presentation by first posing a question. Global estimates for fertilizer nitrogen recovery by crops range from 30 to 50%. So any fertilizer nitrogen not recovered by crops may represent an economic loss to growers, which is important since nitrogen fertilizers account for the highest variable cost in grain production. Ecologically, unrecovered nitrogen may contribute to the nitrogen cascade, with detrimental effects including greenhouse gas production, tropospheric ozone production, nitrogen deposition above critical thresholds, acidification, eutrophication, and stratospheric ozone depletion. Bill Pan has estimated that a 10% improvement in nitrogen use efficiency by wheat in the inland Pacific Northwest may result in a reduction of 78,000 megagrams of CO2 equivalents emitted per year. And so nitrogen management is important. And so the question I will pose is whether unrecovered nitrogen by crops is necessarily lost from the plant soil system, and under what conditions rotational nitrogen recovery may exceed single season estimates of crop nitrogen recovery. To answer these questions, I will begin by reviewing some research conducted by others. Recently, Gardner and Drinkwater performed a meta-analysis and reviewed 217 field-based studies to determine the fate of 15N labeled fertilizers under various management scenarios for grain production. These authors reported that under a wide range of management scenarios, crops recovered 33% of the added fertilizer on average, 22% of which was exported in grain. Now, 38% of the fertilizer was not recovered and presumably lost to leaching and gaseous pathways. However, 29% of the 15N was recovered in soil at harvest, mostly as organic nitrogen. And so there are two important implications of their findings for rotational nitrogen cycling. First, the majority of plant nitrogen was derived from soil organic matter and/or residual nitrogen, ranging from 60 to 70% of the plant nitrogen uptake, and thus highlighting the importance of nitrogen recycling. Secondly, a significant amount of nitrogen may be retained by the soil, which leads to the next question. What effect does the retained nitrogen have on nitrogen storage, nitrogen cycling, and recovery by subsequent crops? So another group of researchers monitored the recovery of 15N labeled fertilizer from a single application over a period of 30 years at 2 site locations. The authors concluded that additions of fertilizers leave a legacy in cropping systems since cumulative leaching persisted over 3 decades, amounting to 12% of the added fertilizer. Likewise, crops continue to take up fertilizer as well, capturing an additional 15% of fertilizers over the next 29 years. Therefore, soils acted as a buffer to reduce leaching losses and as a reservoir for continued crop uptake of residual fertilizers. So from this study, we can conclude that fertilizer nitrogen can be recycled in subsequent seasons. And so for my research, I wanted to look at the residual effects of fertilizer in subsequent seasons. To address this, I monitored nitrogen in the plant soil system for 2 years following spring canola. My research was conducted at 2 sites: Pullman, Washington, which is located in the annual cropping zone, and Davenport, Washington, which is in the transition region, and was replicated by 3 time sequences. The arrows that you see or will see in this figure signify that a measurement was taken, with outputs coming out of the soil and inputs into the soil. So for the results, we found that in a single season, the recovery of nitrogen by spring canola was low at both locations. The apparent fertilizer recovery, as shown here by the red bars, indicates that relative to the unfertilized control, only 18% of the fertilizer, which was added at a rate of 89 kilograms of nitrogen per hectare, was recovered in Pullman, Washington, and 13% recovered by spring canola at Davenport. So when assessing the recovery of total nitrogen supply, as shown by the brown bars, we found that only 44% of the total in supply was recovered in the grain or at soil at harvest in Pullman, and 23% at Davenport. And so we followed these plots into the second year. We planted spring pea and we examined the residual effects of canola fertilization in the previous year. We found that spring pea yielded more nitrogen in plots following fertilized canola at both locations and replicated by year. As a result, the 2-year cumulative recoveries of fertilizer and nitrogen supply was greater than the first year alone, as shown here by the hatch bars. These trends continued in the third year with winter wheat, with apparent fertilizer recovery being enhanced and more efficient recovery of the N supply over a 3-year period versus a 2 and single year period. So now the increase in the recovery efficiency from soil N supply over the 3 years may be partly explained by the crops that we chose to follow the canola. First, peas may enhance N uptake through fixation, while winter wheat was fertilized optimally and exported relatively more nitrogen in its grain than spring crops. However, the increase in apparent fertilizer recovery highlights the importance of residual effects of fertilization, with increases in grain nitrogen outputs in the second and third years following fertilization of canola relative to the unfertilized crop, and this was due to a greater nitrogen availability and recycling from one crop to the next. So far I have shown that fertilizer nitrogen can be recycled, thus affecting nitrogen availability and uptake from one season to the next. However, we have not yet discussed the biggest reservoir of nitrogen in the plant soil system, which is the stock of organic nitrogen stored in soil. Specifically, we need to know the status of this nitrogen in the soil. Is soil organic nitrogen in equilibrium, or is nitrogen being released from soil organic matter at a greater or lesser rate than the fertilizer nitrogen is being retained? A total nitrogen balance like the one presented by Rachel Unger and Dave Huggins in the Year 4 annual report aims to account for all nitrogen present in the soil system in relation to inputs through fertilization and outputs through grain harvest. Now, their approach is to measure soil nitrogen, often in the first foot, to determine changes in nitrogen storage relative to inputs and outputs over time. Now, this approach can work very well over long-term studies where the total nitrogen content of soil can be continuously monitored for net gains or losses to determine whether mineralization and immobilization are in equilibrium or not. However, in short-term studies like REACH, the applicability of the total nitrogen balance is limited. So here I am presenting data for total nitrogen in the top foot of soil, which is on the y-axis, that I collected in 2011, 2012, and 2013 along the x-axis, and the same field at 2 locations, the left being Pullman in the annual cropping zone and the right being Davenport in the transition zone. So as you can see, total nitrogen measurements are often volatile from one year to the next, with great deviation even within a single year following 2 different crops, as you can see here, with winter wheat following pea or wheat. So with such potential error, we need to monitor nitrogen or total nitrogen to assess long-term trends in nitrogen storage. And so therefore, in the short term, we're limited to data for regarding fertilizer inputs, grain nitrogen outputs, and residual soil inorganic nitrogen until we can accumulate enough data points to assess long-term trends. So what can we do for the REACCH region in order to construct nitrogen balances across the different AECs? So how may we compare different crop rotations? Well, Bill Pan and Frank Young have begun working on multiple year nitrogen balances in Ralston, Washington, which is in the grain fallow zone, by dividing outputs by inputs, with outputs being grain nitrogen and final root zone inorganic nitrogen, and inputs being fertilizer and initial inorganic nitrogen. But we must keep in mind that this equation assumes equilibrium in the soil organic nitrogen pool. So for our results to be meaningful, we need to also continuously monitor the soil nitrogen storage, as previously discussed, to verify that the soil nitrogen pool is indeed in equilibrium. If not, a rate of change in soil organic nitrogen should be determined over time and outputs adjusted and rotational nitrogen recoveries reassessed. Over a 5-year period, Bill Pan and Frank Young compared the nitrogen balances in 4 different rotations, being winter wheat fallow, spring wheat Kim fallow, continuous no-till hard red spring wheat, spring barley, and continuous no-till hard red spring wheat. They found that all rotations had nitrogen recoveries greater than 60%, which decreased with increasing inputs. Furthermore, accounting for residual soil nitrogen typically increased the recovery estimates of nitrogen in the system, with the exception of winter wheat fallow, highlighting the importance of accounting for residual nitrogen in addition to grain nitrogen when constructing nitrogen budgets. So as we move forward, rotational estimates of nitrogen recovery will help us assess nitrogen dynamics across various cropping systems. Since soil nitrogen is the major contributor of plant nitrogen nutrition, accounting for soil nitrogen supply is very important. Differences in nitrogen recycling due to the various environmental factors, differences in fertilization, or cropping sequence may affect nitrogen retention and cycling, and thereby nitrogen recovery from fertilizer sources or the total nitrogen supply. However, it is critical to monitor soil organic nitrogen for interpretation purposes, especially if we want to compare rotational estimates versus single season estimates. So what can we expect? Well, rotational estimates should only exceed single season estimates if nitrogen storage is increasing, but not if nitrogen stocks are in equilibrium or decreasing. If there is no change in soil nitrogen storage, the single season estimates should equal rotational estimates. If the soil's nitrogen stocks are decreasing, then our rotational estimates will be less than our single season estimates. This is also important even if we're comparing crop rotations, since the crop rotation may have a differential effect on the soil organic nitrogen pool, thus affecting the estimates. So I'd like to thank you for attending my seminar, and I'd like to thank these various people for helping me along the way, especially Rich Koenig, Dave Huggins, Frank Young, and Ian Burke, as well as the crew and managers at the different site locations. Thank you, and I look forward to our discussion.